Hey everybody, we are back and we're going to pick up where we left off in Chapter 7. So, in the last video, what we did was we looked a little bit about the components that are typically involved in nucleophilic substitutions of alkyl halides, right? We looked at the type of alkyl halides that you can have, we looked at leaving groups, nucleophiles, solvents, etc. Now we're actually going to start looking at the reactions themselves. We're going to start looking at mechanisms, right? What actually happens as we go from a reactant to a product in these reactions, right? So there's a couple of different mechanisms that we're going to learn about. They're called SN2 and SN1. The S stands for substitution. The N, and I don't know why I made this a little n, it should be capitalized. The N stands for nucleophilic, and the numbers 2 and 1, those actually refer to the rate order. So if you remember back in Chapter 6, we talked about kinetics when we wrote rate equations, and we could find the rate order by adding up the exponents of the reagents in the rate equation. This is what that's referring to, right? So we're going to see nucleophilic substitutions that either have second order or first order kinetics. So what I'm going to do is we're going to look first of all at just some sort of inherent characteristics of these mechanisms, right? You know, how many steps they are, the kinetics they follow, stereochemical features, etc. We're also going to take a look to see what types of components, reaction components, work best with these mechanisms, right? Certain alkyl halides work better in SN2 reactions. Others work better in SN1 reactions. Same thing for nucleophiles and solvents, all right? So that's what we're going to do, and we're going to start off with SN2 reactions, all right? Now let me just draw a simple example here of an SN2 reaction, right, involving an alkyl halide. We could have something like this, chloroethane. We can react it with something like sodium methoxide in the presence of acetone, and that will give us a substitution product and a byproduct. Okay, now, first of all, one thing that I want you to recognize, and this is kind of, people get a little bit mixed up on this, so I'm going to try to make it as clear as possible. When we see sodium methoxide, NaOCH3, recognize that is a sodium salt. We will frequently see sodium salts and potassium salts used in these nucleophilic substitutions. All right. Now, if you remember Gen Chem, what happens to sodium salts and potassium salts whenever you put them in a solvent? They dissociate, right? They always completely dissociate. So what you're going to see is actually what happens when we put the sodium methoxide in solution. It dissociates and forms Na plus and OCH3 minus, right? It dissociates in the ions. And the sodium, we care nothing about. Sodium or Na plus or potassium, which is K plus, plays no bearing at all in the reaction mechanism. It does not appear in the products. You can just forget about it altogether. Okay? So please don't write a product that has like sodium in it or something like that. The important part of this is going to be the anion, the OCH3 minus, because that is going to be your nucleophile, right? Nucleophile, nucleus loving, it makes sense that we would be looking at the negative species. Okay? Now, complicating this further is that sometimes you won't see it written as the salt. Sometimes you might just see it literally written as, you know, chloroethane, arrow, and then an OCH3 minus sitting on top. It's just sort of a shorthand way of doing it. Either way is used, either way is acceptable. All right. Now, we don't just have jars of OCH3 minus sitting on the shelf. We do have jars of sodium methoxide. So that's why, you know, it's important to realize that. All right. If we're drawing the mechanism, we can see that if we have a negative O, that's going to be attracted to this carbon, right? Because that carbon has a partial positive since it's attached to an electronegative Cl. So the oxygen's going to attack that carbon. It's going to carry the CH3 with it, and simultaneously, Cl minus is going to act as a leaving group, and it's going to go away. All right? And that is the mechanism. One thing that you'll notice is that this all happens at once. It's one step. Everything happens together. This is going to be very typical of an SN2 reaction. They follow concerted mechanisms. Everything happens together. Okay? All right. Now I'm going to erase this part up here. Actually, I'm going to erase everything and I'm just sort of kind of reallocate my space. So give me a second. Okay, so we know it's a concerted mechanism. All right. Let's go ahead and draw the energy diagram for this. We can draw the energy diagrams. I can tell you the most important thing to recognize with these energy diagrams of SN2 and SN1 reactions is being able to identify the number of steps and also the transition states. Right? You want to be able to know what given species are present at any given place. Don't worry so much about the energy change, whether it's endergonic or exergonic. You're not going to know unless that's given to you. Right? Let me illustrate. All right, so I'm going to do an energy diagram for the reaction I previously illustrated. Okay, I'm going to just go ahead and assume this is an exergonic reaction. So let's just say that it loses energy. All right, so for an SN2 reaction, typically, and I shouldn't really say typically because you will always see this for an SN2 reaction, you're going to see one energy hump, right? One energy spike. All right. That's because everything is concerted. At the very beginning of this reaction, you have your chloroethane, and you also have your nucleophile, which is OCH3 minus. At the end of the reaction, you have your product, right? And you'd also have your byproduct. All right, and you know here, that's where you have your transition state. Well, let's see what's actually going on here. You guys should be able to draw the transition state. Right? Remember, the transition state is basically sort of this little in-between state of things that shows bonds breaking and or bonds forming. Since this is a concerted reaction, all the breaking and the forming of bonds occurs at the same time. Right? So, you have chloroethane, and you're in the middle of breaking. It is surprisingly difficult to draw dotted lines on this whiteboard app. So apologies if it looks a little rough. All right, so you're in the middle of breaking that carbon-Cl bond, and you're also in the middle of forming an OCH3 bond. Right, so you're showing the partial bonds here that get formed. All right. Now, we're not done yet because whenever you draw a transition state, oftentimes there will be partial charges there that you have to take into account. And in this case, we're going to have two partial charges. All right. First of all, let's look at the oxygen. Right. If you look at the oxygen at the beginning in the reactant phase, it's got a full negative charge, right? What about the oxygen at the very end in the products? It's neutral, right? So if you have a full negative and then a charge of 0, the in-between would be a partial negative, and that's kind of where you are right now. You're at the in-between. All right? So oxygen's going to have a partial neg. Cl as well. Chlorine was neutral at the beginning. At the end, it's negative, fully negative, so it's also going to have a partial negative. Put that in brackets, and voila, that is your transition state. All right, so that is something that you should be able to draw. You should be able to draw the transition state for an SN2 reaction and later on for SN1 reactions as well. All right, so let's see. We know it's concerted. I know I keep moving this around, but keep running out of space. We know it's concerted. Let's take a look at the kinetics. we've already said that SN2 reactions follow second order kinetics, right? It's illustrated in the name, SN2. Here's why. All right. Remember, whenever you write a rate equation, you always say rate equals K, and then you have to include the concentration of any reagent that was involved in the rate determining step. Well, SN2 reactions only have one step, right? Everything's concerted. So you're going to need to include any reactants that were involved in that one step. We actually have two. We have the alkyl halide, and we have the nucleophile. All right? So that is your rate equation. All right? And then to get the right order, what we do is we add up the exponents. Now, I told you in the last chapter, you guys kind of have it easy here because anytime you have, for your purposes, anytime you have a reactant in one of these rate equations, it's going to have an exponent of 1. So 1 plus 1 equals 2. And that's why an SN2 reaction is second order. Okay? Hopefully that makes sense. As always, let me know if you have any questions and need some clarification. Okay. All right, so that's 2 features. So if you're keeping your bulleted list on the side here, we have concerted and second order. All right, I want to put another reaction up here, and this time we're going to involve stereochemistry. Let's say we had that. And let's say, again, we're just using methoxide. I'm going to go the shorthand approach here and just go ahead and omit the sodium. I'll use acetone again as a solvent. All right, so again, if we're looking at the reaction here, the reaction mechanism, it's pretty simple. This goes in, attacks that carbon, Cl- leaves. All right. Now, this one's a little bit different, though, because we see that the nucleophilic attack occurs at a stereogenic carbon. Yeah, we have a stereogenic center right there, right? And what happens with SN2 reactions is this. You actually see the stereochemistry change once the nucleophile attacks. It's not going to be on the wedge like that Cl is. It's going to be on a dash. So that is actually going to be the third point that we have in our list. We always get what we call complete inversion of configuration. Sounds fancy schmancy, huh? It basically means that whatever the configuration, the RS configuration was at the beginning, it's going to be the opposite in the product. Here's why. And it's a little bit more difficult to illustrate this without, molecular models. But basically think of it like this. You have a 3-dimensional molecule here. All right, I'm going to redraw this reactant. And then we have the H over here. We didn't draw it in the first structure because skeletal structure, but it's there. And then we have this nucleophile here, this negative OCH3. All right. Whenever we have an SN2 nucleophilic attack, this always occurs via what we call backside attack. What that means is that the nucleophile always comes in from the opposite direction that your leaving group is pointed, right? So the OCH3 doesn't want to come in from the same side as the Cl, right? It always wants to sort of sneak around the back. And because it does this backside attack, it always ends up in the opposite arrangement or the opposite configuration as your leaving group, right? It'll attack from the back, and then it'll sort of bump that H forward. So, if we go up here, if I want to draw the H, it would actually be pointed forward now. Okay? There's a reason for this. There's a reason why we always get backside attack, right? Let's see if you can get it. I'll give yourself a spoiler warning here so you can pause it and try to think about it. I'm sure you all will, hopefully. All right, think of it like this. Look at the charge on the oxygen. It's negative, right? It's fully negative. What about the charge on your Cl? Obviously, it doesn't have a full charge, but does it have a partial charge? Absolutely, right? So you guys know Cl is very electronegative. It's going to have a pretty strong partial negative. So if you were to get front side attack, that means this fully negative O would have to get very, very close to this partially negative Cl, right? What the like charges do when they get close to each other, they repel each other, right? So that's not an electronically stable situation, right? So for that reason, you're always going to get that backside attack, and the end result is that you get complete inversion around that stereogenic center. All right, and we'll do another example or two regarding stereochemistry later on, but if you have any questions about it, again, just let me know. All right, so that was the third thing on our bulleted list, was complete inversion. All right, now the last three have to do with the types of components that are preferred, right? Certain alkyl halides, for example, work better for SN2 reactions. Right? The best types are methyl halides. That's just simply a CH3 that's got a halogen attached. Very, very close to that, though, are going to be your primary alkyl halides. All right? Those work better than secondary alkyl halides. And for all intents and purposes, tertiary alkyl halides are not reactive in SN2 reactions. They're a no-go. I totally butchered that X. There. So methyl halides and primary alkyl halides, they react very, very well. Secondaries are certainly very capable of reacting, but they don't go as fast as the other two. And then tertiaries, they just don't do anything. Okay? Why is that? Well, let's take a look. Let's compare, a primary alkyl halide, something like that, versus a tertiary alkyl halide. And let's say we have a nucleophile out here, OCH3-. We'll just use that one again. All right? Now, think about it this way. In order to form a bond between the oxygen and carbon, this oxygen has to come in pretty close to the carbon before you can actually form a bond and knock off that Cl, right? In which case do you think it's easier to do that? Here or here? Well, you guys know the answer is the top one, right? Just because of context. Yeah, this one, it can't occur. Why? Well, what's the answer when you what answer do you give when you don't know? Half the time it'll be right. So yeah, steric hindrance. Simply speaking, that nucleophile has to navigate a very crowded pathway here in order to get to that central carbon that has a Cl. It can't fit. It's too crowded. Whereas in something like this, which is a primary alkyl halide, you have plenty of room to come in and attack that carbon. The more alkyl groups you get attached to the carbon that's being attacked, that makes it harder and harder for that nucleophile to come in. Right? So that's why you see the order of preference here. You will absolutely want to learn whatever terminology you want to say, the order of reactivity here. Because this is the most important factor in determining whether something is SN2 or SN1. Right? The first thing you look at always is the type of alkyl halide. If you have a primary alkyl halide, it's going to go SN2. It's just not going to go. It's not going to want to go SN1. All right. All right. The second thing to consider here is going to be your nucleophile. SN2 reactions, they work best with strong nucleophiles. It's not impossible to use a weak one, but it's very rare. All right? And again, this makes sense. Why do you need a strong nucleophile? Because look at what it's being attracted to. You're always going to be attracted to not a full, sorry, that should be positive, not negative. You're always going to be attracted to a partial positive. So something like this, here's the new spot of nucleophilic attack. That's a pretty decent partial positive, but it's still a partial positive. It's not a full positive. So the attraction is not that big. So if you had a nucleophile, let's just say water or something like that, that was considered a weak nucleophile, weak nucleophiles oftentimes have pretty weak partial negs on them. So the attraction between here and here would be a very weak one and probably not strong enough to get that reaction to go. For that reason, it's best to have a nice, robust charge on your attacking nucleophile in order for it to fully react. All right, so strong nucleophiles are the preferred nucleophiles of SN2 reactions. Also, SN2 reactions work best with polar aprotic solvents. And this is actually because of what we talked about the other day, right? Whenever you have your nucleophiles, they're always going to be solvated in a solvent cage, right? Whenever you have, a strong nucleophile, such as, OCH3 minus, if you had a protic solvent like water, it would form very strong hydrogen bonds that would be make it very difficult for it to escape that cage, right? So for that reason, whenever you do this, you always want to make sure, if possible, to have nice aprotic solvents, such as acetone or DMSO or THF or whatever. Not impossible for this to work with protic solvents. You can actually do it, but it just goes a lot slower. All right. These three are written in order of importance. Alkyl halides are the most important thing when determining mechanism, then the type of nucleophile, and then the weakest of these is going to be the solvent effect. Okay. One thing that I highly encourage you to make is to either make or find a table that kind of summarizes a lot of this in quick, easy reference form. Because you're going to have to learn not only the conditions that are favorable for SN2, but you're also going to have to learn the ones that are favorable for SN1, which we'll do in just a minute. And then in Chapter 8, you'll have to learn the ones that are most favorable for elimination reactions, E1 and E2. And those are also with alkyl halides. So it can be a lot to kind of sort out. So having a nice organized table will really help you keep everything straight. All right. So let's talk SN1 reactions. Now, as you might expect, SN1 mechanisms are largely the opposite of SN2, right? For one thing, they're stepwise. They're always going to have more than one step. Most of the time, they'll actually have 3 steps, 2 of which are actually part of the substitution, and then a last, deprotonation step. Right? So, for example, let's say you had something like this. You might typically see something like this where you have an alkyl halide, and let's just say it's reacting with water. All right? And this is going to be a substitution in which you end up replacing the Cl with an OH. Okay? Now, unlike the SN2 reaction, this doesn't happen all at once, right? This is stepwise, right? So the very first thing that happens is that your Cl minus leaves. And when it does so, it takes the electrons with it and forms a positive carbon. You guys know that that's called a carbocation. All right? Once you form your carbocation, fully positive charged, then your nucleophile, which is in this case water, can attack. Now, one thing to note with the nucleophiles in SN1 reactions, they are not part of salts. They do not come from sodium salts or potassium salts, so there's no dissociation, right? Water comes in, all of it, leading with the oxygen because it's got the extra electron pairs. All right, and so now water is attached to that carbon. There's one last step that happens, and that is a deprotonation. This positive oxygen will shed one of the H pluses, and it'll give you your products. Okay? So everything's very sequential, stepwise. Not everything happens at once. Now, because of that, of course, your energy diagram is going to look a lot different. Your energy diagram is going to have more than one hump in it, more than one energy hump. How many it has depends on the type of weak nucleophile that you use. Most of the time, probably like 90% of the time, it's going to have 3 humps because you're going to be using a neutral nucleophile to do this, and it requires a deprotonation. That's not absolute, though, and in fact, if you look in your book, you'll see they actually gave you an example where they used a negative nucleophile that was still weak. They used something called the acetate ion. That is a weak nucleophile because that nucleophile is unusually stabilized by resonance. Right? So in that case, you would only have a 2-hump. But in this case, we're going to have a 3-hump diagram, which is the more common state. I'm not going to draw the energy diagram and go over the 2-humped one. You can go over it on your own. If you have any questions on that one, let me know. I'm going to draw a diagram for this one. And again, you don't really know what the energy state is, so I'm just going to sort of tell you, okay, we're going to end up having an exergonic reaction. I will say that the first step is almost always endergonic. So as you make the carbocation, it's going to look something like this. And then you have a smaller energy hump where you sort of get beyond that and the water or the other nucleophile attacks. And then you'll have a third one associated with the deprotonation. All right, so this one's a little bit more complicated looking. Let's take a look and see what species exist where. All right. Remember, in this first reaction, basically you're just doing the deprotonation. So you have your alkyl halide at the beginning. That Cl minus leaves, and it gives you the carbocation. All right, and Cl minus is also there. I'm not going to draw it just because I'm running out of room. And then this carbocation reacts with your nucleophile, which is water. And when it finishes reacting, you have that. And then that last little deprotonation gives you that. Okay? Now, we have 3 transition states, so you need to keep track of your steps and what's actually happening. Think about what's happening in this first step. What are you doing? You're actually just breaking the bond between Cl and carbon. That's all you're doing, right? So, you need to show that. You don't have to worry about the nucleophile because it's not doing anything yet. Come on. Once you get to the top of the screen or the side of the screen, it doesn't like you drawing stuff, so sorry about that. Okay, so that's the bond that we're breaking. Again, we have to keep in mind charges, or partial charges, right? Cl was neutral, and then I guess I should draw this in. You have Cl minus as a byproduct. Cl minus is a byproduct. So you're going from neutral to negative there. So Cl is going to have partial negative. Come on. That's as good as I can get it. All right, and then the carbon that the Cl was attached to started off neutral, but it ends this step as positive. Okay, so this, come on, jeez. Okay, that is transition state 1. All right. All right, then we do the same thing for this hump, right? We have a second transition state. All right, what are we doing? Well, we're taking that carbocation, and now we're forming a bond with that and the oxygen from water. Okay? Carbon in this step started off positive, and it ends up neutral, so carbon again is going to have a partial positive. Oxygen was neutral, ends up positive, so in this one we actually have 2 partial positives. All right, and in the last one we're just simply deprotonating, so we've got this fella, this oxygen, it's got 1 hydrogen attached to it, and we're also breaking the bond with the other hydrogen. Oxygen goes from positive to neutral, so partial positive. I guess I should also mention the fact that we will have an H plus hanging out here as a product. That H goes from neutral to positive, so it also has a partial positive. That is transition state 3. All right. Cool, cool. All right, let's write the rate equation. All right. Now, we saw, again, we'll go back to the bulleted list, we saw that this is, going to follow first order kinetics. Because we know it's in the name, SN1. Why is that? All right, well, let's write the rate equation. Rate equals K, we always have that. Now, we only include the concentration of reagents that are in the rate determining step. Well, when it's concerted like SN2, it's pretty easy, right? Everything's involved. Here, though, we said that the formation of the carbocation is always the slowest step of these reactions. Always. What reactants are available are involved in this? Well, only one, and that's going to be your alkyl halide. So that's your rate equation. It's got an exponent of 1, so that means your overall rate order must be 1. So that's why this follows first order kinetics. All right. Let's take a look at stereochemistry. All right. Let's see. Let's do one like this. All right. All right. So we're doing a different SN1 reaction here. We're going to have that. Just for fun, we'll use methanol. I don't want you to think that water is the only nucleophile we can use. Alcohols are quite often used as nucleophiles as well. All right, so we'll use this one. All right, so let's look at the mechanism. All right, so we know that first thing that's going to happen is that we're going to form a carbocation. So Cl minus has to leave. Okay. All right. One thing I want to note here, I didn't draw the H. I can. I didn't draw the H because of skeletal structure, but it's there. Here's an interesting thing that happens, though. Whenever that Cl minus leaves, that actually changes the hybridization of that carbon, right? This carbon is sp3 at the beginning, so it has a tetrahedral three-dimensional arrangement. However, this one over here, once you form the carbocation, it's only got 3 groups around it right now, so it sort of switches to an sp2 hybridization. And that means the H that's on it is actually no longer on a dash or a wedge, it's just on a straight line. All right? That'll be important for looking, at seeing where the nucleophile attacks. All right, so then you have your CH3OH, and it's going to lead in an attack here. All right. Now, you saw an you saw an SN2 that we always got backside attack, right? We saw that we always got backside attack because we had a negative nucleophile coming into close proximity with a partially negative leaving group, right? And that was bad. Here we have no such restrictions. There's no electronic effects to repel anything. There's no steric effects to repel anything too, because this carbon is sp2 hybridized, it's flat as a sheet of paper, and that means you can get that nucleophile attacking either from the front side or from the back side. Which one happens? They both do. And that means you actually get a mixture of resulting isomers. All right. Now, once you attach that nucleophile, now you have 4 groups around that carbon again, so now you do have to go back to the dash wedge arrangement. So you get this. But you also get this. Okay. And the last thing that happens is that, you'll deprotonate each one of these, and you'll end up with a mixture of stereoisomers. You get that, and this. Come on. And you'll get them in equal amounts. Always. Okay? So the stereochemistry is not quite as well defined with SN1s. You don't just get one particular stereoisomer. You always end up with a mixture of them. So, if we're doing our bulleted point here for stereochemistry, you always get, whenever you attack a stereogenic center, you always get a racemate. Remember, we said a racemate was a 50-50 mix of 50-50 mix of enantiomers, right? So you get a racemate, also known as a racemic mix. Okay. All right. So now we go to the preferences. All right, and again, it's going to follow the same order of importance. Alkyl halides are the most important, followed by nucleophiles, and followed by solvents. It's going to be the opposite here. Tertiary alkyl halides work best, followed by secondary. And for all intents and purposes, primaries and methyl halides don't work, at least not with this mechanism. Okay? Now, the reason for this is not steric hindrance. It has to do with the nature of the carbocation itself. I'm going to make another series here. carbocation stability. Not all carbocations are as stable as other ones. Certain ones are more stable. That means certain ones are easier to form. Tertiary carbocations are the most stable, at least of the ones we've gone over so far, followed by secondary, and then for all intents and purposes, primary and methyl carbocations are very, very unstable. And you see that matches right up with what we saw as far as the type of alkyl halides that work, right? So whenever you're doing this, a tertiary alkyl halide is going to work great for SN1 because its carbocation is stable. That means it's very easy to form, all right? One thing that you'll notice is that it's kind of nice, there's a nice dividing line with tertiaries and then primary / methyls. Primary methyls work great for SN2, work crappy for SN1. They don't work, in fact. The opposite is true for tertiary. Works great with SN1, doesn't work for SN2. The gray area you have is with secondary alkyl halides. They can do either one. And therefore, they're the most challenging to deal with. Not too bad, but still, they offer a little bit more of a challenge. That's why it's important, again, to be able to recognize not only the alkyl halides that you use, but also the nucleophiles and solvents. All right, we saw that strong nucleophiles worked best in SN2 reactions. It's the opposite for SN1. SN1 reactions tend to use weak nucleophiles. You have that full positive charge, so you don't need a strong nucleophile. We also tend to use polar protic solvents with SN1s. And one thing that's kind of interesting is that often one compound will double as both. You notice in the two examples I put, one had water and one had, I think, methanol. I didn't add an additional solvent to those. That's because they were pulling double duty, right? The water, in its reaction, the water was serving both as the weak nucleophile and also as the solvent. Same thing for the methanol. Whereas in an SN2 reaction, that's not something that you really run into. Okay? So there you go. There's the distinction between SN1 and SN2. And so what you need to do, again, is learn these, and then you want to apply them. Work some practice problems and figure out, okay, look at a reaction setup and tell, is this going to be SN1 or is it going to be SN2? All right. I have a few practice problems here I'll work with you, and then you should work a bunch of them on your own. All right. Always take stock of what you have. So let's say I have this. Let's use something different. Let's use acid. Let's use DMSO here. Okay. Now, again, remember the order of importance. All right. The first thing you always look at is the type of alkyl halide. So what type of alkyl halide do you have? Hopefully you've been able to identify this is a primary alkyl halide. We know primary alkyl halides do not work in SN1. We know they work great for SN2, so you can tell right off the bat that's an SN2 reaction. Okay? Your nucleophile, if it's NaCN, remember you get dissociation. Our nucleophile is going to be CN minus. Since it's SN2, everything is concerted. No stereochemistry to deal with here, so we don't have to worry about it. And voila, you have your organic product. Looks like that. Then, of course, Br minus as a byproduct. Okay? You could take this guy. Let's see, we'll put in ethanol here. Again, looking at the alkyl halide, it's a tertiary alkyl halide. We know those only undergo SN1s. So The mechanism has to follow SN1 mechanism, so you're going to form a carbocation. And then your nucleophile will attack. And you'll deprotonate it. Okay, and that's your product. Then, of course, you end up with H plus and I minus as byproducts. Okay? Couple more, then I'll be done. All right, so let's say we have this. We're going to go exotic. We're going to use N3 minus. That's called the azide ion. We'll use some THF here. Okay. Now, looking at this, again, first thing we look at is type of alkyl halide. Now, this is a secondary alkyl halide, right? And we learned that secondary alkyl halides, they can do either one, SN1 or SN2, about equally. So that means we have to look at the nucleophile and solvent that we have. All right. You can refer to your handy-dandy chart of, well-known, commonly used nucleophiles. You can see azide should be on there. This azide, N3- is a strong nucleophile. THF, if you look at your table of solvents, that is a polar aprotic solvent. And both of those should lead you to deduce that, hey, that's probably going to be an SN2 reaction. So that's going to come in, and Br- is going to leave at the same time. Now, this one, if you'll notice, does have a situation where your nucleophile is attacking a stereogenic center. So, what happens to stereogenic centers in an SN2, when stereogenic centers are attacked in an SN2 reaction? You betcha, you get complete inversion of configuration. So that N3 is going to be attached now, but it's going to be pointed on a dash and not a wedge. Note, however, our other stereogenic center, right, the one with the methyl group on the wedge, remains unchanged because, hey, it wasn't attacked, so it just stays the same. Okay? One last one. All right. Now this is another situation where if you look at it, well, I drew those electrons really bad. Sorry about that. If you look at it, what type of alkyl halide do we have? We have a secondary, so it could be SN1 or SN2. We have water here. Water classifies as a weak nucleophile. Also, I did not draw an additional solvent, so that means water is also pulling double duty as solvent as well. That's a weak nucleophile, protic solvent. That means you're going to have an SN1 reaction. So the Cl- leaves to give you a carbocation. Water attacks. Where can that water attack from? You got it. Front or backside, or I guess I should say front and backside. So we end up with this. I'm really painting myself into a corner here. Okay, let me redraw. There we go. So you end up with two directions in which the water is attacking from. Each of those will deprotonate, and as we mentioned, you're going to end up with a racemic mix. All Very good. Okay, so now you're hopefully well equipped. You have a good working, recognition of the difference between SN2 and SN1, and you need to get some practice at applying these concepts. Now you're very well equipped to tackle most of the homework, so go ahead and get going on that. And if you have any questions, let me know. Until next time, I'll talk to you later. Bye-bye.